Hi, I'm Norman Wildberger. Today we're going to look at mathematics' most important function, which is the determinant. The determinant is a function that inputs a matrix and outputs a number. What is a matrix? A matrix is simply, for us today, a square array of numbers. So a table of numbers where the number of rows and columns in that table are equal. The determinant appears in almost all branches of mathematics in one way or another, and it lies at the heart of linear algebra. Today we're going to see some initial applications of how it gets involved in geometry. First of all, what is a determinant? Well, the determinant of a 1 by 1 matrix is just the element inside it. The determinant of a 2 by 2 matrix is given by this very important formula. So the determinant of the matrix A, B, C, D is the number AD minus BC. The 3 by 3 is a little bit more complicated, but still very important. So it's important that you study this well. So here's a matrix with entries A, B, C, D, E, F, G, H, I. And the determinant is a number obtained from these 9 numbers by doing the following. We take A times E times I, that's the first term, and then we subtract A times F times H, and then we add B times F times G, subtract B times D times I, add C times D times H, and subtract C times E times G. So there are 6 terms with plus and minuses in front of them, and that combination is the determinant of the 3 by 3 matrix. It gets more complicated as the matrix gets bigger. Here's the determinant of this 4 by 4 matrix. We're not going to go through it. You can have a look at it. There are 24 terms. Each is a product of 4 different entries of the matrix. And I'll let you have a better look at it now. So what is the general pattern involved in this definition of the determinant? Well, if we have an n by n matrix A, let us say, then the determinant of A is a sum of different terms. So it's a sum of terms, each of which looks like this, a product of n different entries of A. Each of them has a plus or a minus 1 in front of it. And these n entries that we are choosing are not random, not just any n entries. But we only choose these products where there's one element from each row and one element from each column. And we sum over all such choices of n elements of A. So for example, in the 2 by 2 case, AD minus BC. The first term is A times D. That's one entry from each row and each column. The second entry BC, that's also a term that has one entry in each row and each column. In the 3 by 3 case, if we choose, say, one random one, say, let's say BFG, we have 3 n elements, 1 in each row and 1 in each column. In the 4 by 4 case, what this really amounts to, you can think of a checkerboard or a chessboard with 4 rows and 4 columns. And we're placing rooks on this chessboard in such a way that none of the rooks can take each other. So that means there's going to be at most 1 rook in each row and in each column. And we place 4 rooks down. And there are exactly 24 ways of doing that. And so each of those 24 ways of placing a rook down corresponds to one of the 24 terms in the 4 by 4 determinant. And in fact, this one here, if you check, corresponds to the term minus BHIO. That was in that big formula on the previous page. Now there's one extra thing to explain, and that's the plus or minus that is in front of each of the terms. That's actually the most subtle aspect of the whole thing, the plus and minus terms. And how do we know, for example, in this expression that there's going to be a minus sign in front of the BHIO term? Well, what you do roughly is you ask yourself, how many swaps of, say, columns do I need to make to go from this position of rooks to the position where the rooks are all down the diagonal. So in this case here, for example, if we swap these two rooks, then there would be rooks in these two positions. So that one's in the right position. That's one swap. Now let's swap these two. So now we'd have rooks in these two positions. Now that one's in the right spot. We've made two swaps. And then finally we make a swap there to get all four rooks down the diagonal. We've made three swaps. That's an odd number of swaps, so we would put a minus sign. That's the general rule that defines a determinant. And clearly, as the matrix gets bigger, the determinant becomes a pretty complicated expression. But we'll see that there are very beautiful properties that it has that makes understanding determinants simpler than it might first appear. Determinants appear in geometry in two quite different ways. The first way relates to areas and volumes of parallelograms and their three-dimensional generalizations called parallelepipeds. So for example, if you have in the plane a parallelogram whose sides are the vectors AB and CD, so we're talking about this parallelogram right here, then its area can be computed to be AD minus BC. In other words, the determinant of the matrix that you get by putting the vectors along the rows. And in fact, this is not exactly what's usually called the area. It's more the signed area, in the sense that this area can also be negative if the orientation of the vectors is reversed. And there's exactly a corresponding formula for the volume of a three-dimensional analog of a parallelogram involving three vectors. And that's given by a 3 by 3 determinant. The other way that determinants appear in geometry is as a simplifying and unifying ingredient in formulas. A very important expression in rational trigonometry is Archimedes' function, which is what you get when you take the difference between the left and the right-hand side of the triple quad formula. This expression is also 16 times the square of the area of a triangle with quadrances Q, P1, and P2. So usually I write Q1, Q2, and Q3 in discussing the triple quad formula. Here there's a Q and a P1 and a P2. Well, if you'll just accept that for a second, then this quantity being 0 is exactly equivalent to the triple quad formula. It's what we get when we have three collinear points and the three quadrances formed by them, say P1, P2, and Q. And it's very easy for you to check that we can rewrite this as a determinant, as a 2 by 2 determinant, 2P1, 2P2 down the diagonal, and these terms P1 plus P2 minus Q on the off diagonal. So please check that this determinant actually equals this expression here. Now, the three-dimensional analog of that. Now we have 4 points in the plane, forming 6 quadrances. And we're going to arrange things so that there's a triangle with quadrances Q1, Q2, Q3. And our fourth point makes additional quadrances P1, P2, and P3. And now there's an expression or a formula that we'll call Euler's function. So it's a function of these 6 quadrances. And here it is right here. It's a determinant. It's a determinant of a 3 by 3 matrix constructed almost exactly in parallel to this one here. 2P1, 2P2, 2P3 down the diagonal. And then these kind of terms, P1 plus P2 minus Q3 on the off diagonal sides. These are the same. These are the same. And what we're going to see is that the relationship between these 6 quadrances is that the Euler's function takes on the value 0. And when we state it this way, then this important relation between these 6 quadrances is an immediate generalization and extension of this fundamental fact, the triple quad formula, holding for 3 collinear points. So clearly we need to understand determinants a little bit better. We need to find out more of their properties. Next time we'll do that. I hope you'll join me for that. I'm Wildberger. Thanks for listening.